Okay, we're going to pick up here where we left off. And we were in chapter 12, so we started getting into equilibrium. And last time, obviously, we talked about the equilibrium constant, which is K, which always is, no matter really what equilibrium constant you got going on, it is always the concentration of your products divided by the concentration of your reactants. And as we talked about last time, when you do get this, it will really just be a number in most cases, and there's usually no units associated with it. But really, as we talked about, what sort of the value of K will tell you is if you have a large value of K, that means that when you do reach equilibrium, you should mainly have products present. Again, just mathematically speaking, if we take a large number divided by a small number, we will end up with a large number for K. And vice versa, if you end up with a small value of K, that'll tell you when you reach equilibrium, you're mainly going to have probably reactants. Remember that sort of a large value for K is considered 1. So kind of anything above 1 is considered a large value for K. And there is obviously various degrees of sort of large and small, as we'll talk about as we go through the semester. As I might have mentioned last time, you can have a K value just like times 10 to the 34, which is a really, really large number. And you could have a K value that's a really small number, like minus 56 times 10 to the minus 56, so a very, very small number. So you could really have a K value anywhere in between those. But generally, that is what it kind of tells you. Large value, should expect some products there at equilibrium. Small value, more reactants at equilibrium. We talked about a couple of different types of Ks. We have Kc, and we talked about Kp. C, I'm going with concentration for C, and P, I'm going for pressures. So we can definitely write equilibrium expressions both in terms of concentration, and when we do so, typically the concentration should be molarity, which is our moles per liter. And we can do it in terms of pressure. And we can have a Kp essentially if we have gases involved. So if we had, for example, all gases, like we saw a couple of examples last time, we could write a Kp expression. The only difference is, again, instead of using concentration when we would do that, we would use partial pressure. So in this case, we could write Kc would be the concentration of C squared divided by A squared times B. And again, we do take the coefficients as the exponents when we do write it. If we again have something like this where they're all gases, we can then look at pressures as well. And here we could have a Kp, which is the partial pressure here, for example, of C squared. Still need to square it because of the coefficient, divided by the partial pressure squared of A times the partial pressure of B. So you could write a Kc or Kp value. These are two of thousands of K values we're going to talk about. Not really thousands, but it will seem like it as we go through the chapters. One, again, using kind of pressures and one using concentrations. As we talked about as well last time, typically if you're doing any type of equilibrium calculation involving pressures, usually atmospheres is the units that you want to make sure that you're using. So if you're kind of doing the calculation, you want to make sure that you are using atmospheres. There's a relationship to go between the two. So Kp equals Kc RT delta N. Again, that is our Kp pressure equilibrium, concentration equilibrium. That is our gas constant in terms of the ideal gas law, 0.08206. And that is our temperature in Kelvin. And remember, as we talked about last time, delta N is the number of moles of gases. So delta N is really the moles of gases here. And we take the moles of the product gases minus the moles of the reactants. And again, as we talked about, it's really important to make sure that you do it that way. You take products minus reactants. Thank you. Otherwise, you may get a negative number, which is actually really important in terms of the math part of it if you're going to put it into this equation. So you do not want to ignore a negative number you get if you do that. You just don't want to take the difference between, say, both sides. If it's negative, you got to keep that for the math part of it as well. Otherwise, you will get the wrong answer. Also, I think we also talked about it. Typically, when you do the math of this, you want to do that part first before you multiply it by the Kc. So make sure you do that part first before you multiply it by the Kc. We finished up talking about sort of equilibrium reactions and what to do with equilibrium constant values if we sort of change the equation. So if we had, say, K here 1, and let's just say again, we did not need this equation the way it's written, but we actually need the reverse of that equation, which is C and D being our reactants and A and B being our products. We can reverse this reaction. And when we reverse a reaction, as you can see here, if we did an equilibrium expression, for the first one is C times D over A times B. If we did it for this guy here, we'll just call it K2. It is the concentration of A times concentration of B, concentration of C, and the concentration of D. This is essentially 1 over the K value. So if you need to reverse the reaction, you don't change the sign of the K value. You take 1 over the K value to do so. If you need to multiply an equation by a common number, let's just say we needed to multiply this top equation by 3, you do have to multiply the entire equation by 3. So 3a plus 3b gives me 3c plus 3d. Again, if you were to write the equilibrium expression for this guy, it would be c cubed d cubed divided by a cubed and b cubed. And essentially what we just did is we took the first k value and we cubed it, basically, is what we did there. So we multiplied by 3. We take the k value to 3 to get it. So again, you don't multiply the k value by 3 in this particular case, which again is a common error. So you take it to that exponent. Obviously, if we were going in the opposite direction, we wanted the original equation back, and we decided to divide this whole equation by 3, we would end up with a plus b goes back to c plus d. And when we would do that, we would actually take, in this case, the cube root of k3. Again, we divided by 3, we take the root of it. So if you reverse a reaction, you take 1 over the k value if you need the new sort of k value for that reaction. If you multiply by a common number, you take the k value to that common number. And if you divide by a common number, then you, again, take the root, basically, of that common number. The other thing, obviously, is if we had an equation or two equations, and we had two k values for those guys, and we were going to add these together. Let me actually do it this way, make that E and F over here. And let's just say we're going to add these together. What would happen is things on opposite sides of the arrow would cancel out or reduce down. You could kind of think of the arrow like an equal sign, like you're subtracting it to the other side. You would get A plus B goes to M plus N. When we add equations together in terms of the k values, if we're looking for the k value for this guy, we again multiply the k values. So we do not add them, so we multiply them together. You have 3 k values, you multiply 3 of them together. It doesn't matter really how many you have. So again, that's also something that sometimes people mess up on. They commonly want to add instead of multiply those k values together. And I would say when they reverse reactions, they always want to throw like a negative sign and change the sign rather than taking 1 over it. So those are very common sort of errors. Any questions on any of that stuff we talked about last time? All right, we did one example at the end there. So I think this is where we left off. So why don't you give it a go? So we are looking for the k value for this reaction here based on these two equations. Take a few moments, see what you come up with. Yeah. Yeah, you could assume they're all gases. In this case, it's not that important. It's just the reagent there, but yeah. I'll put the not relevant for answering this question. How's that? But if it makes you feel better, you can put G's against the thermal if you like. You could put S's next to them all and don't have nothing to solve for. That'd be good as well. Equation you're looking to get to. So really the best thing to do is just start kind of left to right in the equation you're looking for and try to get everybody on the right side, or the correct side, not really the right side, but the correct side, and make sure you have the right amount. So for me, if I was looking at this, I'm just going to start with this guy N2, which seems like a good place to start. And when I see N2, it's on the left-hand side, and really the only equation that has N2 in it is this guy, and it is on the left-hand side, so that's good to go in terms of that. We also need to make sure we have the right amount of it, so ultimately I need to end up with 2, but right now I only have 1/2 of N2, which means I do need to multiply this by what number? Yeah, 4 would work. And remember that when we do multiply it by 4 or any number, we are multiplying everybody in the equation by that number, so not just the N2. So that's going to get me, if I recopied it, multiplied N2 N2s plus, that's 12 divided by 2. I'm going to go with 6 H2s. Gets me 4 NH3. Now, also really important, since we just did that, that will affect the K value. And in this case, since we are multiplying, that means I should go up with that 4. I should take this guy now to the 4th power. Again, not multiply it by 4, but basically take it to the 4th power in this case. So that takes care of that. The next thing I might want to look at is water, which is right next door. That is also on the left-hand side, and this is the equation where we find water, and it happens to be on the left-hand side. Once again, here, though, we do not have the right amount of them. We need 6. We have 2. So that is going to require us, for the bottom guy here, it looks like, to multiply by 3, I think, in this case. And if I do that, that's going to give me 6 H2Os. Goes to 6 H2s, and it's like 6 3O2s there as we do that. Once again, here we multiply by a common number of 3. So in this case, we do need to take our K value, and in this case, cube the K value. At this point, we're out of equation, so we hopefully did this correctly. So let's just make sure before we continue on, we're going to add these together. Once again, anything on opposite sides of the arrow that's the exact same will completely cancel, or it can also reduce down. So it may not have to completely cancel out, but again, you can kind of subtract it and reduce it down. In this case here, I got something H2s there, and I think actually that is it. And at that point, everybody on the left-hand side of the arrow stays there, and everybody on the right-hand side of the arrow should also stay there. And if I did that right, I should now end up with basically the equation I was looking for, and that looks good, I think, in this case. First off, any questions on that so far? At this point, if I call this, for example, K1 and K2, the K value for this guy should be K1 times K2 here. Again, we're not going to add, but we do need to make sure we're using the adjusted numbers. So that is something as 411 to the 4th power times 0.345 to the 3rd power. So that is going to get me here. I will go with 1.17 times 10 to the 9. And again, individually, we're looking at something like 2.85 times 10 to the 10. And maybe 4.11 times 10 to the minus 2. Once again, we're going to multiply those to get down to that number. Any questions on that there? Small value or large value K? Yeah, super large value. That means we should mainly expect products in this made up example here, and it should definitely head towards the product side in this case. Any questions on manipulating? Yeah. No, so once you do something to those initial equations, then that's what you want to work with for the rest of the problem. And at the end, it should really add up to the overall equation you're looking for. And as you can see here, right, I didn't really have to worry about the other two things in there, right? By multiplying and kind of taking care of like the first couple of things, it actually took care of everybody else in there. And that's very common, these type of problems. You kind of adjust the equation one or two ways. It will kind of take care of like everybody that's involved there, and it should hopefully end up where you need it. You know, other questions? Yeah. It doesn't really matter in this particular example because we already know the K value. We're not trying to find it. Yeah. So if it was a different question, like we needed to find it, then you definitely need to know the states. And I probably would have been more careful and put them in there. But in this case, it wasn't really relevant to the calculation we're doing. But if you want, pretty much all of those are gases. Yeah. So they're all gases. So everybody would be included in the equilibrium expression. No. Yeah. Other questions? Yeah. Yeah, so I would say in this case, really in terms of sig figs, you could kind of go with the only numbers you got, which are the K values in this case. So I wouldn't definitely round it like to one or anything like that. So I'd probably keep it similar to the K values that you have in this case. Because ultimately you are kind of multiplying or dividing here, right? But basically multiplying. So, if you follow kind of the sig fig rules for that, it's basically 3 and 3, which should end up at 3. Yeah, it's really you could go with the lower number on that. And it would be okay. I would probably take both, to be honest with you. I'm probably more interested in the calculation part of it, but I would try to keep it kind of based off of those equilibrium constant numbers. Now, if you were doing maybe some math work with concentrations, you'd probably look more at those than maybe the equilibrium constant. Other questions? All right. So we've talked about this now. So just to kind of summarize the stuff that we've been talking about, obviously, as we talked about, if we're dealing with anything with concentrations, molarity is really the concentration that you want to use. Atmospheres for pressure, and we're going to do some equilibrium calculations shortly. And definitely, if you're doing any type of calculations involving pressures, you should convert them to atmospheres and do the calculation. Again, even if they kind of give it to you, say like in millimeters of mercury, and they want the answer in millimeters of mercury, if you're going to do something like an ice table like we will do, you should put it in atmospheres in the table and then convert it at the end of your calculation. So this is kind of important to do it that way. As we talked about, no solids or liquids included in the equilibrium expression. That again leaves you pretty much aqueous and gas. No units associated with it. And as we talked about, when you see an equilibrium constant, it is specific for exactly how the equation is written. What's the reactants? What's the products? Especially for that at that particular temperature. As we'll talk about, really, temperature is the only thing that can affect the actual value of the equilibrium constant if you change the temperature. And as we saw there, if you add equations together, we're going to multiply the K values. And obviously, if you divide, we're going to take it to the root and square it or take it to that power, depending on what you are multiplying by. We also talked about as well a couple of important ideas for equilibrium. I just mentioned the temperature is a really important one. And the idea that confuses a lot of people, which is you can have various amounts of reactants or products when you're doing an experiment that reaches equilibrium. And the equilibrium constant should be the same value regardless of if you started with all products, all reactants, a little bit of everybody in the pot, mix it around together. It should come to rest at the same value for the equilibrium constant as long as the temperature remains the same in all your trials. That was the example I think I did of I want an equilibrium constant of 2, right? If I could write 2. And we could get to obviously by taking 4 divided by 2. We could get to by taking 2 divided by 1. We could get to by taking 8 divided by 4. That's all the math I know, but they all equal 2, and they're all different numbers, right? So the idea is the proportion of products to reactants, as long as you don't change the temperature, will always come to the same ratio, regardless of how much you start with. So it's a very common mistake that people think that, like in this experiment, I started with twice as much reactants. I should have a different K value than I did, say, in the first one. And that's not the case. Again, that ratio of products to reactants will remain the same as long as you don't touch the temperature. And temperature changes it from one temperature comparison to the other. So if you did 5 experiments at 25 degrees Celsius, all the K values should really be the same, regardless of what you're starting with. If you change the temperature to 40 degrees and did 5 experiments, they all should be pretty much the same K value at 40 degrees. But when you compare 25 to 40, they will be different values. What's that? It depends on the reaction. It really kind of depends on the reaction, and also if it's exothermic, endothermic, and those type of factors will come into play as well. Yeah. Other questions? All right. So the next thing we're going to talk about is the reaction quotient, which is actually a different letter for once. So our small break of K very shortly here. So the reaction quotient is Q. And Q is actually calculated the same as K. So Q is calculated the same as K. And that means Q is also the concentration of your products divided by your reactants. So if Q is calculated the same as K, what do we use Q for? Well, there's really two sort of situations where you would look at Q. One I would call kind of just a straight up Q type question. And what Q will tell you is if you calculate Q, it will tell you, is your system at equilibrium at that moment? So the reason you might be doing that is you're given some concentrations. You're not sure if they're initial concentrations, equilibrium concentrations, what type of concentrations they are. So you could calculate Q and it will tell you this simple answer is yes or no. You're either at equilibrium right at that moment or you're not. The second thing that it will tell you in terms of Q is if you are not at equilibrium, which way you need to go to reach equilibrium. Do you need to make more products to get to equilibrium? Do you need to make more reactants to get to equilibrium? And that's basically what Q will tell you. So if you calculate Q and it is greater than the K value, then the system is not at equilibrium. And in order to reach equilibrium, you need to make more reactants, basically. If you calculate Q and it is equal to the K value, then that tells you that your system right there is at equilibrium, basically. If you calculate Q and it's less than the K value, it tells you that your system is not at equilibrium. And in order to reach equilibrium, you actually need to make more products. So if you think about a reaction, we have reactants goes to products, right? So if you write all your Q's on the left and your K's on the right, and as Q is less than K, it goes opposite away that guy is pointing. So pointing to the right, it goes to the left, which is reactants. Here, pointing to the left, it goes away from it, is going to make more products. So that's a way that you can sort of remember it if you want to do it that way. But that is what Q will tell you. You calculate Q, it will tell you if you're at equilibrium, and it'll also tell you if you're not at equilibrium, which way you need to go to reach equilibrium. Any questions on that there? In order to calculate Q, you would need all the concentrations of everybody involved, right? So there would be no way for you to calculate Q if you are not given all the concentrations. So that's one way to know whether or not you should calculate Q is, do you have enough information to actually do it? So if you don't have enough information, you can't calculate Q. But if you are given enough information about everybody in the reaction and you can calculate Q, then you probably should. So there is a Q problem, which is like this, which is it at equilibrium? If not, which way to go? The second place where you should calculate Q is, as we'll talk about a little bit later, when you're doing equilibrium calculations, because if you're not at equilibrium, you might want to know which way the reaction is going to the reactions or products, because it might make an effect or it might affect the way that you calculate your sort of calculation. We'll talk about that a little bit later on. Any questions on that? Just like K, only aqueous and gases go into Q. So it's basically done exactly, it's basically K with a Q instead of K, basically, is how it is, basically. All right, so let's give it a go there. If you start with 0.249 moles of N2, 3.21 times 10 to the minus 2 moles of H2, and 6.42 times 10 to the minus 4 moles of NH3 in a 3.5 liter vessel. The Kc is 1.2. First question is it at equilibrium? Second question, if not, which way do you need to go to get to equilibrium? Take a few moments there, calculate it up. We don't have the molarity given to us of everything, but we definitely can calculate it. We got moles, we have liters, so that basically is molarity. So we can get to the molarity. And when we look at, we can get to the molarity of everybody here. So that does allow us to calculate Q. And that's really what we want to kind of look at to see if it is at equilibrium. We are given the K value, so we have something to compare it to. So once again, as I mentioned before, Q is pretty much the same as K in terms of how you calculate it. So here we would go the concentration of NH3. We do need to square it because of the coefficient, just like normal. We will divide it by the concentration of N2 and the concentration of H2. And once again, here we would need to cube it because of the coefficient there as well. So we do need to get the molarity to go into our Q expression. So let's do that. So our concentration here of N2 would be our moles, which is 0.249 moles divided by 3.5 liters. And that's going to get us there a number 0.0711, we'll call it. We'll do the same thing for our H2. And we'll take the moles of our H2, 3.21 times 10 to the minus 2 moles, divided by our 3.5 liters. Make sure you use your exponent button and punching it in. Going to get us a 0.00917 molar. And lastly, we got some NH3 there. And I'll go up here. NH3. We take the moles of that, which is 6.42 times 10 to the minus 4 moles, divided by our 3.5 liters. And that's going to get us here. I'll go 0.000183 molar. Now that we have the concentrations of everybody, we're good to go and to put them into here and calculate our Q. So our Q in this case would be our NH3, 0.000183. We're going to, again, square it here, divided by our concentration of our N2, 0.0711, and 0.00917 for our H2, which does need to be cubed. So popping that into your calculator correctly, do a little bit of that. We're going to square the top guy, divide by the bottom. Don't forget to hit equals. Divide by the next bottom guy, open a parentheses, 0.00917 and square it, close your parentheses. And you should get a number here. And in this case, make sure I hit the right number there. Just double check mine here. There we go. Divided by 0.0711 and 0.00917 cubed. There we go. Try that number. I think we end up with 0.611, we'll call it here, as our Q in this case. Yeah. Any questions on that there? In this case, first off, Q is less than or greater than? It is less than K. That tells us, is the system at equilibrium? So no for the equilibrium. Now it tells us also which way do we need to go to reach equilibrium. Yeah, we need to go opposite of where that's pointing. We need to go towards the product side, right? Going in that direction. And we need to make more products in this case to reach equilibrium. Any questions on that? Yeah. Yeah, so essentially what you have is sort of like, if you want to think about it, kind of like an imbalance to what it needs to be at equilibrium. So in this case, we actually would have kind of a little bit more reactants than products. So actually, there's kind of this graphical thing here. So if Q is less than K, it would go to the product. So you kind of have a little bit less reactants in products. So it's going to cause the forward reaction really to occur. And it's going to start to kind of build out some more products. And the opposite is true on this side here. In this case, you actually would kind of have a little bit more products than reactants. And since you're not at equilibrium, that means the rate isn't equaling each other at that point. So because of the availability of the products, for example, the second example there of having more products than reactants, that's going to cause a reverse reaction basically to occur. As we sort of talked about the other day, right? So the availability of products or reactants more on one side or the other will cause you the forward reaction or the reverse reaction to go if you're not at equilibrium or is trying to get to equilibrium. Yep. Other questions? Okay. All right, then that brings us to really what this class is all about, and that is just turn the page and be done with it. So that is solving equilibrium problems. So remember that if you have the equilibrium expression and you want to calculate it, you do need equilibrium concentrations to do so or equilibrium pressures to do so. And if you are not given equilibrium concentrations or equilibrium pressures, and you have more initial concentrations or pressures, you actually need to calculate what your equilibrium pressures or concentrations would be. The way that we do that is we use what is referred to as an ICE table. ICE meaning initial, change, and equilibrium. As I write through all the words there. Now, you might have used ICE tables to do something like limiting reagents. If you took me, you did. If you didn't take me, you probably didn't. Maybe, I don't know, or maybe you did. But there we kind of use end and a little bit different, but sort of the same sort of idea in terms of the calculation. So when we have initial concentrations, we really need to figure out what's going on in this reaction, which way is it proceeding, and really what the change is going to be. So ultimately in these calculations, we use X to represent the change. And ultimately when we do these calculations, that is what we're trying to find, which is what is the value of X. So try to figure out what is the change that's going on in this reaction and really what we're left with when we reach equilibrium. So for example, you know, if we had an equation like 2a plus b goes to say 3c. And let's just say initially, you know, A, we had 2 molar and B, we had 3 molar given to us. And we wanted to know kind of what is everybody's equilibrium concentrations. So if we were going to do this, we would use an ICE table. And first off, an ICE table doesn't work if you don't have an equation, which as we talked about earlier, really important in this class to be able to write equations. Otherwise, you're kind of stuck looking at your ICE table with no equation. So make sure, again, that you have it. Like any equation, it should be balanced, or this is not going to work right either. So always need a balanced equation when you do it. So initially here, if we were going to do our ICE table, we would use our I, and we would basically put in our concentrations, 2 molar and 3 molar. Now, nothing was given to us in terms of C, right, initially. So if you're not given anything in terms of products, for example, it is safe to assume that it is 0 in this particular case, yeah? Now, clearly, if you're given something on the product side, you should put a number there, right? So if you're not given anything, it is safe to assume that it is 0. Now, because of that, we also can make a pretty safe assumption that if you had to take a guess, would this reaction head in the forward direction or the reverse direction? Yeah, because the only thing we have available to us is reactants, right? So the only thing that can start to react are the reactants, which means that definitely should kick off really the forward direction of this reaction. That's really important in the table for the change part, which is the C part. That's because if this reaction is heading towards the product side, should I have more or less reactants over time? I should have less, right? There's only way to get to the products, right? They should be decreasing. The way we represent that in an ICE table is that is with minuses or subtract but numbers or whatever you want to put it. But we're basically going to minus our reactants. And as time goes on, we then should see our products start to go up, right? Because we're obviously making more products. And those are represented in the ICE table with pluses. So minuses on things decreasing, pluses on things that are increasing. The other super important part of this is everybody's favorite thing, stoichiometry, dare I say it, and the mole to mole relationship, right? So you got to take that into account as well. So this would be minus 2x, and the 2 is the coefficient. That 2 takes care of all the fun mole to mole relationship, all bundled together for free, and you don't have to do it separately or anything like that. If you don't use the coefficient, you will get the wrong answer. So again, really important, the equation is balanced. Make sure that you use that. Obviously, no coefficient there, so it's 1. So you could just go minus x in this case. Here we have 3, and that's our product. So that's going to be plus 3x in this particular case. That is the change part. That is really the most important part of it. Now, when we're done here, we could drop our equilibrium line, and that would basically be 2 minus 2x, 3 minus x, and 3x. First off, any questions on how to set up that ice table? Yeah. We know based on the initial information given to us, which is we only had reactants given to us. So the only possible way this reaction could proceed at that moment is reactants go into products. So we don't have no products to go the other way. So it has to go in the forward direction, which means if it's going in the forward direction, we should be making products, which means our reactants should be decreasing, which is why they're minuses. Our products should be increasing, which is why they're positives. Yep. Other questions? All right. So what do we do with this now that we have that? We could just look at it. No, we will take our equilibrium expression here, and we will do it like normal, c to the third power divided by a squared and b. And normally in this type of problem, you would probably be given an equilibrium constant. Hey, we'll just go for 50, why not? And that would equal 50. So what we do at this point is we take our equilibrium line here, and everything in the equilibrium line gets put into our expression. So we take these guys and we put it in there, and then we solve for x, which is the fun part of the program, maybe the math part of the program. So at some point you will solve for x, and we're going to talk about a few different ways that you could solve for x. Probably the most complicated way that we will solve for x in here is the quadratic equation. That's like an ax squared plus a bx plus a c is equal to 0, where the quadratic equals x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Semi-familiar? Not to me, but semi-familiar to you. So that would probably be the most complicated way that we will do it. And by the way, when you use the quadratic, how many x's do you get? Yeah, you should get 2x values, right? And in this case, we'll talk about it, but one of those x values will not work or make sense, and one will work. So you won't use both. Obviously, you'll use whichever one is good. Now, there's some other ways to solve it, which we'll talk about as well. Now, when you do solve for x, however you go about solving for x, why that is really important is that is the change that's really happening. And the x that you eventually get to when you solve for it, if you go back to your equilibrium line, that is every single x in your equilibrium line. So because you now know what the change is, you can now put it into the equilibrium line and actually get numbers of what the concentrations are at equilibrium for everybody. Questions on that? Obviously, we're going to do some examples in just a bit here. Any questions on that? If you're doing this table and you're doing it with concentration, once again, it should be molarity. We will later on do this table with moles, which can be done, but right now you should do molarity is probably the best bet. If you're doing this with pressure, which you absolutely can do, this is what I was talking about earlier, atmospheres when you go into this ice table. It needs to be in atmospheres. Once again, even if they give it to you in some other unit and want the answer in some other unit, you have to atmosphere it up and put it in that table and then convert it at the end. So it's really important to make sure it goes atmospheres into this table. Our friend Q that we just talked about, right? Q tells us, nice highlighter Q there. Q tells us that is the system at equilibrium, right? It also tells us if it is not at equilibrium, which way it needs to go to reach equilibrium, right? If you come across an equilibrium problem like this and you can calculate Q, you should calculate Q, because what part of the ice table would it affect? for example. Yeah. Yeah, so for example, let's say I calculated Q and I found I'm not at equilibrium, which probably would be the case if I'm doing an equilibrium problem like this. But it tells me that I need to go towards reactants rather than products. What would change in this case? It is the change part of the table, right? So if this reaction actually needs to go this way, this guy would no longer be plus, he would be minuses, and these guys would be pluses, right? So it would affect the change part of it if you calculate Q and it tells you need to go to the reactant side. I would say probably 99 times out of 100, you could probably just autopilot going to the product side, but it can eventually sometimes maybe head in the opposite direction. So if you could calculate Q, that is the second place where you would need to calculate Q is doing an equilibrium problem like this, where you got to decide, okay, if it's not at equilibrium, which way it needs to go. So you're kind of doing the ice table correctly. And the first way of doing Q is what we just did earlier there, just a straight up, is it at equilibrium, which way it needs to go? Any questions on that there? All right, so let's do one here together, see if I remember how to do it. All right, so the concentration equilibrium constant for this reaction is 7, lucky number 7. If we initially start with a Br2 concentration of 0.663, we want to know what is everybody's equilibrium concentrations. So first off, in this case, could I calculate Q? The answer is no, because you don't have everybody's information, right? So there's no possible way for you to calculate Q, so you don't have to worry about it, right? So we're just going to jump into our ice table. I'm just going to rewrite the, maybe, let's see here. No. All right, so I will rewrite the equation there so I can see it. Get rid of my scribble. There we go. All right, so we're just going to rewrite it down here, a little Br2 going to 2Br. We could write our expression, our Kc in this case would be the concentration of Br, and it would be squared, divided by Br2, and this equals lucky number 7 there, right? So we're going to do our ice table here. So initially, the only concentration that's given to us is the Br2, so 0.663. And once again, in this case, nothing is mentioned about our products. So if there's nothing mentioned about the products, it is safe to assume that it is going to be 0 in this case. Any questions on that there? Also, because there's no products, I could probably safely assume this reaction should be heading in which direction? Yeah, it should be going towards the products, right? Because all we got is reactants. That's going to tell us that our minuses in this case should be on the left, right? And our pluses should be on the right. So that is the change part. That's a minus x because the coefficient is 1. That is a plus 2x because the coefficient is 2. That's going to bring us to our equilibrium, which is 0.663 minus x and 2x. First off, any questions on the table here? Now that we have our equilibrium, what we're going to do is basically we want to solve for x. And we're going to do that by taking our guys and basically putting them into our equilibrium expression. So in this case, our k would equal our 2x, and we do need to square it, divided by 0.663 minus x equals 7. To solve this, I need to do what with the thing on the bottom there? I need to take it to the other side and multiply it, right? I also could square the top, so that will give me 4x squared, which is this guy, right? Is going to equal if I turn the calculator on, probably works better. 0.663 times 7. 4.641 minus 7x. Once again here, we want to bring everybody to the same side to get us into our quadratic, because that is where we're going with this. Does it really matter which way you go? The answer is no, but most people try to keep the first guy positive, the x squared part positive. Doesn't really matter, but that's usually what people do. So what I'm going to do is take all these guys and bring it back to the other side. So that would give me 4x squared. That's going to be plus 7x minus 4.641 equals 0. Again, I added the 7x to the other side. I subtracted the 4.641 to the other side, and that equals 0. That is for our quadratic, our alphabet soup. That is our A, B, and C in this case. Any questions on that there? By the way, you do keep the negative with the C, for example, yes, when you go into there. All right, so why not dust off those math skills? Let's give it a go. That's going to give us, again, x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. So popping this in here, x is going to equal negative b, which is negative 7, plus or minus. If you pop all that into the square root part, that's going to be 7 squared minus 4 times a, which is 4, times c, which is negative 4.641. And let me grab the right pen there. Inside the square root, 123.256. If you do a little square root action on it, you get an 11.102 if you square root it. So that is what you should get inside, and then after you square root it. Divided by 2 times a, which is 8, right? 2 times 4. That's going to give us our 2 x values in this case, right? So we're going to do the plus first, and then go back and do this subtracting. So that's going to be minus 7 plus 11.102 divided by 8 gets us 0.513 as an x value. 0.513, again, doing the plus way. Now we're going to do the subtraction way. Minus 7 minus 11.102 divided by 8 gets us a negative 2.263. First off, any questions on either of those? These are our 2 possible x values. By the way, when you do the quadratic, you could get a positive and negative value. You get 2 positive values. You could get 2 negative values as well. One of them should be good. One of them should be bad. Which one would be bad in this case, you think? It would be the negative, because these x values that we see here are basically these x values in our equilibrium line, which means this is 2 times x. So if I take 2 times a negative number, that's going to give me a negative concentration, which is no good. Can't have negative, yeah? So it's a good thing to remember in this class. Can't have negative. Even though you want to write negative, don't do it. You can't have a negative concentration or pressure. So because that's actually a negative, and basically it's not really because it's a negative value, but it's because when I put it back into the equilibrium, I get a negative value. So that's really important to remember. This is not going to be our correct x value in this case. That would mean that this x value here should be our correct one. And now we're ready to actually solve for our concentrations. So the concentration of Br2 at equilibrium, 0.663 minus x, which is 0.663 minus 0.513. And that is going to get us there 0.15. Oh, I think 0. We got there 15. We will do it there for our BR, and that is equal to 2 times x, which is 2 times 0.513. It's going to be 1.026 or 1.03 if you like to round a little bit. And these should be our equilibrium concentrations in this case, yeah. First off, any questions on that there? Yeah. There's always 2 possible answers when you do the quadratic. Is because of this part of it. So basically when you do the math of it, you do it the plus first, and then you go back and do it the minus. It doesn't. It just gives you, in this case, it's just mathematically, you always get two possible answers for it. And in terms of the equation, one will be good and one will be bad. And again, the way that you know it's going to be a bad one is it will always give you kind of like a negative concentration at equilibrium, which you can't have. Yeah. Yeah. You shouldn't come across that. It shouldn't. I would say probably in most cases you made a mistake. Yeah. Yeah. But I will say it is possible in certain situations that, again, you can get two negative numbers, where somebody sometimes thinks I must have screwed up. I got two negative numbers. But oddly, sometimes if you put it into the equilibrium line, it'll actually turn it into a positive number. So it is possible when we do something like KSP, sometimes that happens, that you actually can get two negative numbers. But and when you put it in, that will turn, one of them will turn into a positive, the other one will stay at negative. Yeah. Other questions? So this is math. Good stuff. But because it's math, right? That means that you could probably check, did you maybe screw up? Which might be a good thing to check. How could I check if I maybe screwed up or didn't screw up? These are now the equilibrium concentrations, right? Which means if I put it into my equilibrium expression, what number should I get? Just get 7, yeah, or pretty close to 7. Now, if you put that back in and you get 420, you screwed up, yeah, for sure. So you can actually put those numbers back in. For example, if you put our numbers back in, you get like 7.07 with rounding. Obviously, it's not going to be probably right on the nose, but it should definitely be in the ballpark. So I would highly recommend, if you got some time after doing it, stick those numbers back in and make sure you didn't screw up along the way. Any questions on that? Now, not every problem will require the quadratic, but that's sort of how you do it. Some a little easier than other quadratics, but we'll see some. Any questions? All right, well then, now that I'm warmed up, you go for it. We want the equilibrium concentrations of everybody here for this equation. K value is 54.3, and we got 0.5 moles of H2, 0.5 moles of I2 in a 1 liter flask. What is everybody's equilibrium concentration? So see what you come up with. All power. Okay, so let's take a look, see how you're doing. So obviously here we can start with our equilibrium expression. So once again, we're going to do our products over reactants. So a little HI. Again, we do need to square it because of the coefficient. We'll divide it by the concentration of H2 and a little I2 concentration for good measure times 54.3. In this case, we were giving moles and liters, which means we can get to molarity. We can get to molarity of H and I. Nothing really mentioned about this guy. So once again, that does eliminate even really the idea of solving for Q, because we can't do it. We don't have enough information. So we could just kind of safely make some assumptions in this problem and not have to worry too much about it. Also, this is not too bad in terms of getting the concentration, since it is 1 liter. So the concentration of H2 would be 0.5 moles over 1 liter. And that's going to give me 0.5 molar for my H2. And pretty much identical there for my I2 will give me 0.5 moles over 1 liter, 0.5 molar. Any questions on that so far? All right, I'm going to flop the page here and go with that. All right, so our K here, copy it here. And that is 54.3. All right, so we'll do our ice table here. That's going to be a 0.5, a 0.5. And once again, nothing mentioned about the products. So again, safe to assume 0 on the product side. Once again, that also gives us kind of a safe assumption that this reaction, it really has only one way that it could be heading in this case, since all we have are reactants. So our minuses should be on our reactant side, our pluses here again should be on our product side. Again, I would say 9 times out of 10, that's probably what you're going to see. That's going to be minus x, and again, we do need to make sure coefficient here on the product side, that's going to be a plus 2x. Any questions on that there? Bringing this down here. 0.5 minus x, 0.5 minus x, and a 2x. Questions on the ICE table here. So again, really pretty much in these calculations, the goal is to solve for x. So to do that, we're going to take our equilibrium line and basically put it into our expression here. So if we do that, that's going to give us 2x, and it's going to be squared, divided by 0.5 minus x, 0.5 minus x, and that's going to equal our 54.3. So again, we just basically put our equilibrium line into our expression. At this point, we do want to solve it. So you could do a little factoring and stuff like that if you got nothing but time on your hand, but we do want to look for maybe easier ways to do that, and hopefully you recognized it. Yes? Yeah, so you could do a little square root action on both sides because it is basically 0.5 minus x squared, right? So this is actually a perfect square on both sides, which you do not want to quadratic that, right? You want to save that for the next example, right? So this one, you don't want to do it. So again, if you quadratic, by the way, should end up the same deal at the end, just a little bit more work. But in this case, some cases in this class, you want to take the shorter approach if it's easier. And it's acceptable to do so. Sometimes it is not acceptable to do so, and you have to do it the other way. But in this case, it is. So that will give us 2x divided by 0.5 minus x. And the thing I personally always forget to do is actually square root the 54. So make sure you actually square root that 54 point, whatever it is there, 54.3. That's going to give us a 7.3689. Once again here, much easier to solve at this point. We're going to multiply that to the other side. That's going to give us a 2x on the left. A little distribution action there. Going to give us a 3.6844. Taking a few extra digits just so we don't get any rounding type errors. At this point, we want to combine our x's. So in this case, we're going to add this to the other side. And that's going to get us a 9.3689x is equal to 3.6844. We're then going to divide that guy back to the other side. And that is going to get us there a number with some numbers. That's going to give us an x is equal to 0.393 in this case. Any questions on that there? All right, so in this case, that is going to be our x value since we didn't quadratic, so we only got one x, so we might as well use it. That once again is every single x value that we see in this table. That is pretty much what that x value equals. So that would give us the concentration of H2 is equal to 0.5 minus x. That's going to be 0.5 molar minus our 0.393 molar. And that's going to get us there. 107 looks like. 0.107 molar. Our I2 will actually be identical to that. So our I2 will also be 0.5 molar minus 0.393 molar. That will also equal 0.107 molar. And lastly, let's maybe go up here. Our HI at equilibrium is 2 times X. So that would be 2 times 0.393 molar. And that's going to get us 2 times 0.393. 0.786 molar. By the way, these are concentrations. They do need units. Yeah, so they need some molarity on those guys. And that would be our equilibrium concentrations. Once again, you could check yourself by putting these values back in. So if you took the 0.786 and squared it, divided by 0.107, divided by 0.107, get about 53.9654. Yeah. Say it one more time. Sure. Yeah, so you got the 0.393, I'm assuming. So you did the quadratic? Yeah. So again, yeah, good example. You will get the same answer if you did the quadratic. By the way, you can always roll quadratic on any of these, as we'll talk about throughout the semester here. And you should get the same answer. The reason you know the other number, which was, what was it, 0.8686. This number is no good because when we put that back into here, for example, what type of number do we end up with? Yeah, so that's how you know it's no good. So again, as I was saying earlier, when you do the quadratic, you can get two positives, you get a positive and negative, and can get two negatives. It's not necessarily, the X value that is positive or negative that is making it good or bad. It's actually when you put it back into the equilibrium line, you will end up with one of those equilibrium guys being negative, and that is obviously the one not to use. So a lot of times it's easy to identify when you got the positive negative value, because if you have something like X or 2X at the end there, obviously that's going to turn that into a negative. So that's not going to work and stuff like that. Other questions on that there. So again, this is a second way that you could solve these. You could quadratic it. You got something that is actually a perfect square on both sides, you could square root it. Or as you saw, you could also quadratic it as well and get the answer, and it should come out the same. Other questions on that? All right, good times here. This example, since we don't have time really to do it, I would like you to do it at home. I'll give you a hint. It's quadratic. Yeah. Some factoring, some good math practice. And we will go over the answer at the beginning on Thursday. We'll go through it on Thursday at the beginning. So do yourself a favor, give it a go yourself before you get here so that you can see how you did. Yeah. So this one, I'll give you a hint. It is quadratic. Yeah. So a lot of good math. All right. Any other questions on anything we're talking about? Yeah. You can start working on probably chapter 12. Again, the homework problems are in the exam 1 module. It'll say exam 1 homework, and it'll list the problems and stuff. Yeah.